Hello everyone, in this video we are going to see one numerical on tapered plate. Now here in this numerical a tapered plate is given whose value of E, that is Young's modulus, is given 2 into 10 raised to 5 Newton per mm square, and it is loaded by 50 Newton force in downward direction. Now we have to model this bar using the two linears per element, and we have to determine stresses in each element, first thing that we need to find out, and second the support reaction. Now this tapered bar having the length of 100 mm, area at bigger end is 800 mm square, and area at smaller end is 400 mm square. Length is given 100 mm, and now we have to find out the stresses in each element as well as support reaction by using penalty approach. In previous numerical we have used the elimination approach, where whatever node is fixed we simply cancel that particular row as well as particular column, but here it is specifically mentioned that we have to solve this numerical by using penalty approach. So we will see how to solve this kind of numerical. So first step is discretization. So in this numerical it is given that we have to divide it into two elements. So this particular length 100 mm is now divided into L1 50 and L2 is also 50. So this will be our element number 1. This will be element number 1. This is first element and here is second element. So now this particular element is divided into two components. First of length 50, second of length 50. Now if you are talking about the node point, this will be node point number 1, here will be node point number 2, and here is node point number 3. Now we have to find out, here area is given 800 mm square, here area is given as 400 mm square. So now we will find out area at this location. So simply how we can find out this area? Simply we can find out this area as it is a center portion 800 mm square plus 400 divided by 2. So it will become 600 mm square. Now we are having the area at this location is 600 mm square. Total length is 100, and we are now finding we have find the area at the length of 50 from this top section. So it is 600 mm square. Now we have to find out the average area for this section. We have to find out the average area for the element number 1, average area for element number 2. So average area for element number 1 and average area for element number 2 will be 600 for element number 1, 600 plus 800 divided by 2, and similarly for this 400, this particular value, plus 600 divided by 2. It will give us the average area. So here 1400 divided by 2, so it will be 700 mm square, and it will be 500 mm square. So in this way we have find out the area of element number 1 as well as element number 2, because these areas are necessary to calculate the stiffness matrix. Now the next thing that we are going to see is the element connectivity, which is a very important step while solving the numerical. So element connectivity, we have to draw the table. Here element number, here are two elements are there, 1 and 2. Now we have to write down the global node number of local node 1 and local node 2. So if you observe here, the element number 1 is connected between 1 to 2, element number 2 is connected between 2 to 3. So simply element number 1 is connected between 1 to 2 and it is connected between 2 to 3. So we have got our element connectivity. Now we will find out the total degree of freedom. Total degree of freedom for this given structure. How to find out total degree of freedom? Number of nodes. So number of nodes are 1, 2, 3. Number of nodes are 3 into the degree of freedom per node. As it is a 1D problem, so degree of freedom per node is 1. So 3 into 1 is equal to 3 is our total degree of freedom. So what will be the dimension of stiffness matrix? Dimension of stiffness matrix will be 3 by 3 as it is n. This total degree of freedom is denoted with n. So we are getting here n into n. The dimension of force vector n into 1, so it will be 3 by 1, and the dimension of nodal displacement vector, so it will be also n into 1, so it will become 3 by 1. So in this way we have found out the total degree of freedom. Now the next step and the formula is the force. We have using this relationship, force is equal to stiffness into nodal displacement. So first thing that we have to find out is the global stiffness matrix. As here in this case 2 elements are there, so global stiffness matrix can be found out by K1 plus K2. So we will now find out the K1 and K2. I am directly writing here. First I will write here the formula for K, that is stiffness matrix. So it is, if you are taking K as outside, 1 minus 1 minus 1 1. And how to find out this value of K? K is equal to AE by L. So for first element K1 is equal to A1 E1 upon L1. So area for first element, we have just found out that area for first element is 700 mm square. So 700 into value of E, it is given in the numerical. Value of E is 2 into 10 raised to 5. So it is value 2 into 10 raised to 5 divided by L1, area length of first element. Similarly we have to find out K2, A2 E2 upon L2. So area of second element, it is 500 into 2 into 10 raised to 5 value of E divided by L2, and L2 is also 50. So after calculation you will get these values as the value for K1, it is 28 into 10 raised to 5. So value of K1 we are getting as 28 into 10 raised to 5, and the value for K2 is 20 into 10 raised to 5. I will request everybody to please pause this video and check these calculations. So now I will combine this. K is equal to K1 plus K2. So while calculating K1, I am having the value of stiffness as 28 into 10 raised to 5. So I will keep 10 raised to 5 outside the bracket. So 28 into 1, 28. Here will be minus 28, minus 28, 28. From element connectivity table, we will quickly check the degree of freedom for the first element. So for degree of freedom for first element, it is 1 to 2, and for second it is between 2 to 3. So we will write here degree of freedom as 1 2 1 2 plus 10 raised to 5 will be out of bracket, and the value of K2 we have got is 20. So 20 minus 20 minus 20 20. And here the degree of freedom will be, in this case it is 2 3 2 3. So now we will do the addition of these two. So for the addition, as we have find out here, the dimension of global stiffness matrix will be 3 by 3. So its addition will be addition of these two matrix will be 3 by 3. Its output will be 3 by 3. So I will draw here the 3 by 3 matrix 1 2 3 1 2 3. Now the location of this, it is in first row first column. So I will write here 28, 10 raised to 5 will be out of bracket. Here first row second column. So here will be 28, its will be here 28, and here its location is second row second column, so 28. Similarly now here it is written 2 3 2 3. So here it will fix in this location. So 28 plus this 20, so it will become 48. So this particular value will become 48. Here will be minus 20, here will be minus 20, 20, and the remaining will be 0. So in this way we have got our global stiffness matrix. Now the formula is F is equal to, here we have written F is equal to, so force vector will be F1, F2, F3, and the nodal displacement vector will be here U1, U2 and U3. So now F1, F2, F3 we have got here. Now we want to write the value. So at node number 1 here reaction is acting, no force at node number 2, and at node number 3 force of 50 Newton is acting. So considering this force of 50 Newton and the reaction force, we will replace this value as at node number 1 reaction force is there. So at node number 1 reaction force is given, but here as we are solving with it with a penalty approach, as there is no force at node number 1, we will keep as 0. No force at node number 2, we will keep it at 0, and here force of 50 Newton is acting. Similarly here U1, U2 and U3 we have written. Now please focus here. Now we have to use here penalty approach. So in penalty approach what we consider, just understand the theory first, that in penalty approach instead of fixed support, what we consider here, spring of large stiffness is added. Now whenever the stiffness of spring is very large, the displacement is very minimum and it is nearly equal to the fixed support. So this is the concept of penalty approach. So now the large stiffness, so in this case it will be like this. Here instead of this fixed support, what is considered here, that a spring of large stiffness is added, and this spring of large stiffness, its stiffness is decided such that its stiffness is maximum of Kij. Now K stands for our stiffness matrix. So maximum value that we observed in case of this stiffness value, so maximum value that I am observing here is 48. So here the maximum value 48 into 10 raised to 5, which is out of bracket, and we have to again increase by this formula. Formula is to find out the stiffness, maximum of Kij into 10 raised to 4. So such a high value of stiffness spring we are considering here. So ultimately displacement that we will get will be equal to 0. So this is nothing but penalty approach, and whenever in numerical it is specifically mentioned that you have to solve this numerical by penalty approach, then and then only we have to go with penalty approach, or else you can use here our, if it is not mentioned in numerical that by which method we have to solve, then simply you can use the elimination approach. So our value of stiffness 28 into 10 raised to 5 into 10 raised to 4, such a value, large value of stiffness we have to add here. Now where we have to add, it is very important thing that we have to add this value at a particular row which is fixed. Now in this numerical the first row, first node point was fixed, so we will add diagonally this value to the first element. So it will be 28 plus this particular value 48 into 10 raised to 4. 10 raised to 5 will be out of bracket, so it will become 48 and adding 1, 2, 3, 4 zeros for this 10 raised to 4. So this value will become 28 plus 48, 1, 2, 3, 4, 0. So now we will solve this numerical. So this will become, I will write it again so that it will be very easy for us to do the calculation for this, and we have to find out u1, u2 and u3. So it will become, I will change its color, 48 0 0 28. Now this become our first element in this global stiffness matrix. So what we have done, we have added the maximum value from this global stiffness matrix which was 48 into 10 raised to 5. We have again divided it, again multiplied it with 10 raised to 4, so that this value is become very large, and ultimately we are going to get this value as 0. So this is about the penalty approach. So now quickly we will solve this. So first row that we will get is 0 is equal to we have to simply multiply. So we are multiplying first row with first column. So while multiplying the first row with first column, what we will get here, 480028 into this first element u1 minus 28 u2. It will become, third element will become 0. Similarly for second, 0 is equal to minus 28 u1 plus this particular value 48 u2 and minus 20 u3. Similarly here 50 is equal to now what will multiply this third row with first column. So 0 into u1, it will become 0, so I will write down here 0 u1 minus 20 u2 plus 20 u3. So I will request everybody to please pause this video here and find out the value of u1, u2 and u3 that you are getting. So values of u1, u2 and u3 that are available with me, I will write down here. I hope that everybody have calculated this value. Value of u1 that I am getting is 1.04167 into 10 raised to minus 9. So just a minute, we have to here at every place we have to consider this 10 raised to 5. Please take care, topmost care of this 10 raised to 5, because if we are going to miss this 10 raised to 5, which is we have kept outside this bracket, then our answers will become wrong. So u1 value that I am getting here, please let me know in the comment section that whether you are getting the same value. u2 is equal to that I am getting here 1.7858 into 10 raised to minus 5, and value of u3, that is displacement of node number 3, is 4.2858 into 10 raised to minus 5 mm. So these are the values that we are getting here for u1, u2 as well as u3. Now the next thing that we need, we will quickly calculate here, because we want to find out these two values here, stresses in each element and support reaction. So simply we will calculate first the support reaction whenever you are using penalty approach. Now if you observe here, please take a note of this. As the node number 1 was fixed, what are value of u1 that we are getting here? u1 is equal to 1.04167 into 10 raised to minus 9. So this value is such a large value which is nearly equal to 0 mm. So in this way we have to find out the u1, u2, u3 by using penalty approach. So when you are using the reaction force, when we want to find the reaction force, it is calculated as minus c into u1. So minus c, the stiffness that we have added, so that value was minus 48, 1, 2, 3, 4 zeros into 10 raised to 5 into value of u1. So value of u1 that we are getting 1.04167 into 10 raised to minus 9. So please do this calculation. Values that I am getting here are is equal to minus 50 Newton. So this is a reaction force which will act at this location, as this particular node point was fixed. So whenever any node point is fixed, we will get reaction there. So the last thing that we need to find out here now is the stresses in each element, and for this stresses in each element we know the formula. So we need formula, so I will first write down the formula to find out stresses in each element. So sigma is equal to E into B un. So the value for B, L into minus 1 1, this E is as it is, into for first here will be un. So for first element, we will find out for first element stresses for first element. Sigma 1 is equal to E1 L1 minus 1 1. First element is connected between u1 and u2. So I am writing here u1 u2. Similarly, I will write down the formula for element number 2. E2 L2 minus 1 1. Now the second element is connected between node 2 and node 3. So here it will be u2 u3. Now the value of E, it is given in the numerical, that 2 into 10 raised to 5. So 2 into 10 raised to 5 we will consider here. 2 into 10 raised to 5 divided by length of first element, which is 50. Here minus 1. Here will be 1 into u1 and u2. Now value of u1 that we have got here, we have to write down here. So value of u1, if you check here, the value of u1 is 1.04167 into 10 raised to minus 9. This value we have to consider here. So this particular value 1.04167 into 10 raised to minus 9, and value of u2 that we are getting here 1.7858 into 10 raised to minus 5. Please try to calculate. Please try to calculate, dear students, and put your name in the chat box, so that I will in the comment section, so I will consider it as your attendance for this lecture, as we are now almost completed this lecture. So u2, value of u2 1.7858 into 10 raised to minus 5, and u3, the value of u3 that we are getting here, let me check, yes, 4.2. Here it is, value of u3, it is 4.2858, 4.2858 into 10 raised to minus 5. So please do these calculations. What we have to do here, first calculate this particular value, multiply minus 1 first element from this row to first element to this column, plus addition of these two. Second element from the row, multiply it with the second column, and find out the stresses in first element. So whatever values are available with me, please check. That stresses for first element that we are getting 0.0714 Newton per mm square. This is the value of stress. Similarly, sigma 2 will be 0.1 Newton per mm square. So in this way, we have to find out the stresses, reaction force using the penalty approach. The only change in the previous numericals that we have solved and this particular element is, in elimination approach we simply cancel the first, if we have solved this numerical by using elimination approach, we have to simply cancel the first row and first column. So 3 by 3 matrix will be converted into 2 by 2. If you compare the elimination approach and penalty approach, elimination approach is very easy to solve the numericals, but in penalty approach we have to add one stiffness, which is very large value, to the particular node point, particular element where we have got this particular in the numerical, that particular node point is fixed. So here in this numerical, first node point was fixed, so we have added that particular value into first place. So this is all about this numerical. Thank you so much.